To give you a reminder of what to expect this morning, we're going to have 2 plenary sessions. The first one is now, and will feature 2 speakers, one of whom, Željko, is going to come up to introduce, and then I'll follow that up. And then after the coffee break, we're going to have a session with a lot of talks from both project-affiliated and from community members on LSST's observing strategy. So that's all I want to say. Željko, please come on up and introduce our special visitor.
Good morning. It is a pleasure to introduce our special guest and speaker, Stasa Milojevic. Stasa is a professor of informatics at the School of Informatics and Computing at Indiana University. And she does many things, but her most recent work is very relevant to our collaboration. She obtained her PhD in information science at UCLA and her undergrad degree in English language and literature from the University of Belgrade. Last time when I visited Indiana University, she showed me some empirical studies about large collaborations with emphasis on astronomical collaborations, and it clicked immediately because it just looked like what we've been doing for the last 10 years. And then she developed models that relate astronomical collaborations to physics collaborations, and she uncovered some very simple but very revealing relationships. So I said, you have to come to our meeting and tell us about it. So here she is.
Okay. Thank you, Željko, and thank you all for having me here. It's a great pleasure. And it's also always fun to present your work to the audience, which is really not your immediate peers. But it's also somehow like knowing that you're talking to people whom you actually studied. It's like as if you're now talking to all of your galaxies and stars. So, let me say a little bit about why astronomy. So Željko said I am an information scientist, but my sub-area is something called science of science. So actually what I'm interested in is revealing how science works, like what are the processes that make contemporary science work, and I do that by looking into the publications that scientists publish. That's the most common way in which science of science works. And for those of you who are not familiar, actually, you are one of the most studied cases of science for those of us who study science. And there is actually a very good reason for that. First, you're well established, right? So for people who are interested in longitudinal studies, you're a great example, right? Like there is a lot of years and lots of data in which you can follow what's happening. Also, your bibliographical data is very easy to define. Actually, you also may be aware of this, but you are one of the poster childs for really doing great scholarly communication work, like sharing your publications, sharing the data, and so on. And also, so you have one of the first repositories which actually do work, unlike some others that started later. In addition, which is something that's very, very unusual, you published in few main journals. And that's not normally the case. Normally, the publication record is spread out among like tens of journals. And for astronomy, it's really 4 major journals that cover 80% of all astronomy, which is, again, highly unusual. Something that's good for us, but maybe when you go for evaluation, not so good for you, you're not so interdisciplinary. At least not so far. I mean, you may collaborate with engineers, but in general, astronomy is fairly well self-contained. And what's really also excellent about this is that you cover a whole spectrum of the ways of doing science, from solo theoretical work to very, very large teams, such as this one, and also with good experimental components. So what I'm going to talk about today are the results that were based, the empirical part comes from the following data. So it's from the 4 journals that I've already mentioned, which publish 80% of all of the astronomy research. So it's Astronomical Journal, Astrophysical Journal, Monthly Notices in Astronomy and Astrophysics. I'm using only a few components of that, and from 1960s to 2009, which is when most of the study actually ends in that data, there were 150,000 articles. And then for the second part of the talk, I go back to the late 19th century and there are 30,000 additional articles. Before I go on talking about the model, this is just what the productivity in astronomy looks like. So you could see that in the 60s, let me see if this works or not. So in the 60s, you actually maybe had a chance to read most of what was published at the time. And you could see that in 2015, there were 9,000 papers published only in that 1 year. So it's speeding up in terms of the productivity. In terms of the number of people doing astronomy, it's also accelerating rapidly. You could see that the acceleration starts in the 70s, but really picks up in the 90s. There is something I introduced here which will be relevant for the remainder of the talk, and that is the notion of a lead author. So all authors mean all of the people who have been listed as authors on a paper, and a lead author would be either a first author and or corresponding author if the name is different. So you could see that the lead authors, the number of those is smaller, obviously, and it's not growing as quickly. For those who are entering the field, I think the competition is getting stiffer because these are just the new authors, and you can see that the number is rising. So for every retired author, 2 new appear, right? So that's the rate in which the number of authors are increasing. Okay, this is just setting the scene of what the astronomy or the publication in astronomy looks like. But then what became of more interest to me is how collaborative teams form and evolve. So again, for you this is obvious, but science is a collaborative effort. And while you were all doing this for a very, very long time, Jacques said for at least 10 years, at least here, a lot of the sciences actually, a lot of the other sciences are now actually going more towards that model of knowledge production. And for people who want to understand collaboration, there are ways, excuse me, in which you can have ethnographers come and observe how you work. And I know some of you were actually hosted an ethnographer who actually looked what is happening in day-to-day life of collaboration. But if you really want to study collaboration over a very, very long period of time, you have to rely on co-authorship data, right? That's the only record of what collaborations produced. It's not a perfect record. Not all of the collaborators end up as co-authors, and some of the co-authors might have not contributed a lot, but more or less it's a good proxy of the collaboration. And number of co-authors on a paper really is the proxy of the size of a research team. And research team is a very, very important unit of analysis. Because again, mostly when we talk of collaboration, we think individual, and then we think this huge collaboration, but there are actually teams, which are somewhere in between. And very large collaborations usually have multiple smaller teams. So for people who studied teams, and this is something that has been done for a while now, there are a few things that became obvious. So teams are becoming more dominant, meaning that there are fewer and fewer single-authored papers. So it's becoming a rarity to see something like that. Teams also growing in size, and what's more important, high-impact papers, meaning papers that attract lots of citations, are more likely to be authored by teams, and even more likely to be authored by large teams than small teams. And furthermore, inter-institutional teams and international teams are doing even better in terms of the impact of their work. And something that's even more interesting, if you're not interested just in the impact as citations, but the intellectual contribution, the novelty, very large teams are also more likely to produce novel results. So teams are really good, but then how do they form and how do they evolve? Is it really that simple? Most of the studies that I mentioned, they just looked at averages, right? So if you look at the average number of co-authors, you see that that number has increased. But that finding has a really, really large assumption buried in it, and that is that the nature of the collaboration hasn't changed, right? It's just that the size has grown, but the way we work is the same, it's just we do more of what we've done before. Furthermore, when they look into describing the distribution, they really focused on power law tails. They really disregard what's happening in the like small team part, which is, it depends what you want to learn, but it may be problematic because 90% of all of the papers are still published in this part that has been completely ignored by researchers. So I was working on another paper which was looking into the referencing practices of astronomers, and I needed to check something, and then I produced this distribution on the left-hand side. This is the number of authors per paper in 61 to 65. And then I look at it, it's like, oh, this looks very, very different from anything I've seen. So this really doesn't look anything that as what we've been studying for so long. Because what we've been studying is what you see in 2006, 2010. And you can see the power law tail. And the 6165 is really well described by the Poissonian function. So it seems that the mechanisms, so what this actually revealed is that it's not just that the mean or the average has changed and it has grown from 1.5 to 3.7 authors, and if you just like give that number, it's revealing, but not as revealing as you look at the whole distribution and see that the nature of how the collaborations form have actually changed. So if you're wondering, well, is this unique to astronomy? Like, is this just something that like we see now? Well, actually, no. It seems that physics looks pretty much the same. It went through this just 20 years before you guys did. So physics in 41 to 45 has very, very similar looking distribution to the astronomy in the 61-65 year period. And now its power law tail, it's even more pronounced than it is for astronomy. So this actually seems that this is an indication that the team formation is essentially a Poisson process, which has somehow transformed to have this preferential attachment growing power law tail. And a question then that arises is, well, is this Poissonian process still present? And if so, how much? And in order to figure that out, and it seemed it was, just because of this area that I call the hook, right, where you do observe a different behavior. So the idea was, well, can we model this? So I set out to do a computational model, which is kind of in a family of something called agent-based models, where you actually produce the simulation following particular criteria. And this is the model that I created that should be able to reproduce how we have this current state and the change. So the way the model works, you do have, as I say, a lead author, right? And the lead author sets to write a paper, and then he or she starts with something called a core team. A core team has the probability of like being drawn from the Poissonian distribution, so it's fairly small, and it can be the size of 1, right? So you can have a core team that is just yourself. And these teams that are called core teams are something that most of us use when we want to address so-called standard problems in astronomy. Like it's a problem where you may not need extra expertise or huge instruments, right? Something that requires gathering a large number of people, but something that you can do either on your own or in your lab or with a few students. And that standard research questions and core teams, which are really Poissonian driven, they don't change that much in time, except when someone retires and that team gets disassembled and replaced by the others. I know that's somewhat a simplification, but actually it works on a model as well, really well. So together with these core teams, or in parallel with them, some researchers realize that they need way more resources to answer the questions that they want to have answered, so they cannot continue working in the core team. So they start assembling so-called extended team. So the initial extended team is just core team, which starts then attracting other core teams. And the way they grow, or the very, very successful, or the more successful extended teams, come from lead authors and core teams that have been very, very productive. So actually, in the past, when researchers explained power law formation, the description was that these are star scientists. Like, you have a star who is very well known, and then everybody else wants to work with that star just because they're well known, and they come to the lab and other people come to it. But this model is actually different. It says it's not so much the star quality, it's really how productive you were. So people and teams that were very, very productive tend to attract more people and become even more productive in the process. So again, if this were a piece of advice, if you're just entering, the good bet would be to come to the lead authors who are very, very productive, and they're more likely then to become member of very, very productive both core teams and also extended teams. And these teams will grow faster and during the cumulative advantage. But what is also very interesting is that these extended teams and core teams exist at the same time. So it depends on the type of the question you want to answer. As an author, you may tap into your core team or your extended team depending on what it is that you're trying to do at a particular moment. So they, like, each author can actually, or each researcher can have multiple teams exist at the same time. So this was the simulation that I ran, and the solid lines are the results of the simulation, and dots are actual empirical data, and they have error bars. So you can see that the model really very well explains the behavior in different time periods. You can also see that the error bars are really, really large towards the very end, and that's because there are very, very few papers in those areas, especially early on. So in 61, 65, there might have been just a handful of papers. The largest team size in 61 was 8 people. The average team size was 1.5, whereas now you have couple of hundred authors in the largest team. You can also see that in 2006 and 2010, in the power law tail, there is this area which doesn't really match. And when you look into that, it's Fermi collaboration that in a very, very short time period put out a number of papers at the same time, and the model the empirical data picked it up, but the model couldn't predict, of course, that the Fermi is going in a single year to publish a lot of papers. So far I said that there are these two types of teams, core and extended, but in order to really, like, when I fitted the data, there was still part that seemed not to be well explained. And that was the occurrence of two authored papers. So in the earlier periods, if you look, the single author paper was the dominant number, like, of authors you would have. But then sometime in the 70s, two author papers take over. And that's what I call core plus one. And most of those, when you look into the data, empirical data, you can see that these are the papers from the first-time authors accompanied with a senior author. And that's really the advisor-advisee pairs. Obviously, sometimes in 70s, start publish a lot together, rather than maybe advisee publishing on her or his own. And that may be just a result of the norms, but that's something that actually became very, very important. So core plus one teams. Here you can see the relative contribution of each of those types of teams to the whole distribution. So you can see that the core teams are really, really prominent in this, what I call the hook area, and that you don't have any core teams that are larger than 10, and then both core plus 1 and extended obviously start at 2, but you can see that extended become really, really prominent in the power law tail, and another confirmation that this may be advisor-advisees pairs is that after 3 authors, this core plus 1 really drops significantly. So that's like for people who are interested in social science, this may be also a very interesting phenomenon, just looking at the practices and norms. So, of course, one can do all of the simulations to try to figure out what's happening with the data, but if you really want to use this model as a component of some other type of the analysis, that's not fairly practical because it does take a while to run the models. What was really nice that there is the functional description of these different team types, and it has 6 parameters, and it has pretty much, it corresponds to like 3 types of processes. So it's Poisson plus 1, and then it's a truncated power law. So like this analytical or functional form really allows one to decompose the distribution or any sort of the collaboration distribution. This here was actually, so once I figured out that there is an analytical function, it became much easier to apply this to all time periods and not just like a few that I was doing up to that point. So on the left-hand side, you can actually see the relative contribution of these different modes of knowledge production to the productions of papers in astronomy. What is very, very interesting is that the core teams have been, or the contribution of the core teams to the astronomical publications was very constant. It's around 60%, and it has been around 60% from 1960 onwards. The contribution of the extended teams have been around 30%. What is really interesting is that obviously in astronomy, starting in 60, there was this need for extended teams, but the extended teams at that time were much, much smaller than they are today. But obviously this need for having like that other mode existed at the same rate throughout at least this 50-year history. And the last line here is core plus 1, and this also may confirm that that's more of a norm, that sometimes in the 70s, if you were a student, like in the 70s, you started putting your advisor on the papers. I actually presented my results to the astronomy department at Indiana, and there were a few people in the audience and said, "Oh, I do remember that. When I was a grad student, we never put the advisor, but when I became professor, that became a norm. Like all of my students put my name, and then they started thinking like, oh, when did that happen? So again, from the social science perspective, that may be something that's very interesting. So that is the relative contribution of the sizes of the teams. Remember that if you just present, let's say, the average number of authors in astronomy grow from 1.5 to 6.7, that might have not been that meaningful, but if you actually see here the rise, so the core teams were around 1 author in 60s, and they grew all the way to 2.3 authors, so even the core teams became larger, right? Even the core teams, but they are really growing at a much, much slower pace. And then the extended teams grew from 2.1 to 11.6. So it's really, when you look at that number, the average number, it's really grown by the exponential rise in the sizes of extended teams. It's the extended teams who really, really grew extensively, and not so much the core teams. So I have shown you some of the physics results, but you may be wondering, like, okay, there are similarities between physics and astronomy. What is happening with other fields? You can see Mathematics, it's still in the 40s and 60s of physics and astronomy. It looks pretty much like they did 50 years ago. And when you do the decomposition for the mathematics, what's really interesting is that in mathematics, the fastest growing component is core plus one. It's not extended teams. Like the core teams are dropping, or the contribution of the core teams is somewhat dropping, and the core teams in mathematics are one, more or less, but their core plus one is really significantly growing. You can see that in ecology and social psychology, you can start seeing the power law taking effect. And then I used archive, which is, like, I know you all use archive, I do too, but archive is dominated by physics. So you can see actually that it looks similar to astronomy, but again, a little bit more pronounced power law tail. So the conclusion was that the story is not that simple. It's really not that these extended teams and just occur on their own, or somebody has an initiative and you just can bring people together and they start working. Like, you do have to have core teams that are already very well established and productive, and then these teams really then start merging and forming. And that can also be very important for science policy and funding, especially with the dwindling resources, when, like, you need to decide who to fund, and core teams do still have a role, although what they produce is not that visible or not that attractive oftentimes. So the second question I had was this, like, role of small teams in big science era. So in the 60s, and like that was when big science actually started. And it did start in high energy physics, but you can actually see in biomedical research, again, not in the 60s, but much later, you do see like occurrence of big science, but in lots of the other fields, you can have elements of big science as well. So to recap, in 1960s, single author, like that, 90% of all of the papers in the 60s published by single authors, which is really today only less than 10% of all of the papers in astronomy are single author papers. And the mean time size went from 1.5 to around 7. So the question is the small team mode of knowledge production a thing of past? And is society wasting resources continuing to funding these who work alone or few collaborators? I know you may argue yes, but as I said, okay, small teams are seeds for large teams, right? So you can you can still fund large collaborations and then foster small teams for that purpose. But then the idea is, what is it that they actually contribute to science? And some people found that they are more impactful, right? Because they have more citations. But then I was like, okay, science is really not citations, and it's not number of publications. And luckily it's not. Like, imagine if our knowledge really has grown exponentially, we would still be in school, I guess, all studying whatever, like just to catch up, or what the textbooks would look like if the actual knowledge has grown exponentially. But like, we do publish more and more. So the idea is there some other measure that would be closer to what we mean by science? And by science, we really mean more like units of knowledge, right, or concepts. And how can we measure that from what we produce? So there is currently no metric for that cognitive contact or the intellectual contributions. We don't we just count people, count publications, count journals, but not really, don't try to count the intellectual contribution. So that's the next thing I try to do, which is I try to use, again, the more of a big data approach to measure the cognitive extent by parsing the titles of the articles and trying to identify how many unique phrases there are in titles. And it took a while, and it's not that easy because the problem is there are more and more papers, right? So if you take as a unit of analysis a year, of course the cognitive extent would be great just because there are more titles and more words. So that wouldn't work. Titles have also increased a lot themselves. So not only we wrote less, we have much shorter titles before. Now we keep adding. It's another thing that has extended. So even if the number of papers is the same, the titles have grown, so you have more words, therefore you're more likely to encounter unique words, therefore the measure wouldn't work. So I really spent quite a lot of time figuring out, okay, what would be the unit that would keep the number of phrases constant and yet give me some sense. So it turns out that the best measure is around 10,000 unique phrases, which corresponds roughly to 1,000 titles. So every 1,000 titles, I count again. So in the earlier periods, there is only a single data point, right? Because there weren't that many articles. But in the more recent periods, if you count that way, there are lots of individual points just for that 1 year, because there are multiple, there are 9 points in 2015, right? Because there are 9,000 papers that were published. So how do you, and the idea here is, so if the science covers a large territory, that will mean that it covers a lot of unique phrases, right? It deals with lots of unique objects with the same amount of papers, or it can have a more focused approach where they really all deal with only a few or a fewer number of concepts. So how do you do that? How do you parse the titles? It turns out that it's not that difficult. What you do is, there is something called stop words or general words. So these are the words that are used a lot in English language, and they don't have that much meaning. There are around 500 of them, like these are articles, prepositions, and so on. So if you use those general, and there are some words that don't have that much meaning in science itself, but they do have in English language in general, such as study, analysis, result, determination. So some of those, so I use those general words as breakpoints between the phrases. Another breakpoint between the phrases is any punctuation. So you have a colon, or if you have like a comma, that would delimit the phrases. So here are examples of two titles. So you have halos, that would be one phrase, and voids. Voids would be a different phrase, and multifractal model would be a phrase itself, and then cosmic structure would be, like in that particular title, there would be those 4 phrases. In the next one, you could see collision strength, one, electron impact excitation is another, and fine structure levels, another one. To avoid something that is really, like a comment I've heard, well, but you know, in sciences such as astronomy, they find a lot of objects, right? It's not really that it's an actual concept, it's just they found the more stuff, and they name that stuff, and therefore it seems that they're doing more. It's like, well, I know, I've heard that. It's like, no, they're actually, no, it's the actual intellectual content. It's not just that they take advantage of the things that they can still discover. So in order to avoid that comment, what I did was I excluded anything that had numbers in it. So I said, no, actually they are doing. It's not that they're just observing stuff and then cheating. What is really good with this model also is that you can count both the individual words and phrases. So one example is you have old words such as mass and energy, which appeared on their own, but then all of a sudden you have a phrase, mass energy equivalence, right? And that phrase you count on its own, right? But there are still papers that discuss only mass or only energy, and these are maintained. Another thing is, I told you that the titles are getting longer. Another thing is, because they are so long, they are also, the phrases get really, really long. So some of the titles have 7-word phrases in them, I know, it's a really long, so it's adjective after adjective after adjective after adjective. So actually what I did is I limited the unique phrase to 3-word phrases, and I use only the last 3 words because like the others are more adjective describing the last 3 words. So that counts to the phrase. So, okay. If you look into astronomy this way, this is how it developed. So actually, there seem to be 4 separate phases, and this goes back to the 1880s. So like this goes back to I think it's the earliest volumes I could find for astronomy. So you could actually see the first phase when it ends when, in a way, astrophysics comes into the scene, and then you can see the kind of increase in the number of unique terms because, again, it was very, very novel. And then after the introduction of astrophysics, the growth is more, I mean, it grows, but it's more or less flat until the 50s and Sputnik. And that's pretty much, that's similar. I unfortunately don't show physics here, but I can. Physics has the similar growth pattern, but except one problem. Physics has experienced a drop in the 70s. Astronomy hasn't. So 70s have been really, I guess, notorious for like a decrease in funding. So there is 50s and 60s, money flows to science, and then in the 70s, there are some problems. So in the 70s, there were fewer students, and I think there was some cutting in funding. And in physics, you can see that. I guess astronomy wasn't as sensitive to the research and development component, so it really did not experience that dip in the 70s and continued growing. And you can see, so what I told you that for each time period there are more dots, but you can see that they actually mattered words because these are randomly drawn 1,000 titles, and they still actually are not dispersed all over the map. So using this method, what's really interesting, if you give me 1,000 titles from the similar period, I can tell you what period it is from based on where it would fit on the line. It's a really, really interesting and powerful method. So I used it to show how, like, what are the phases of the development. It can also, this notion that knowledge grows exponentially would be based on the graph that you see down there. So if you show that, that's just the number of papers. But if you really look at the intellectual content, yes, it did grow, but it's more of a linear growth of science, and that's more in line what we would expect of how science would develop, and not exponentially. So this method, I was then interested, okay, going back to that question, teams are awesome, large teams are even better, but like, do they, like, what it is that they contribute? And the thing is that they contribute a lot, but they actually, if we were not to have individuals or very small teams, we would lose a lot of the cognitive extent because single authors and large teams cover much larger territory, meaning they cover more topics. They're more diverse. They study a wider range of topics, whereas very, very large, like large extended teams, which are like over 100, like over 50 authors, they cover only around 85% of the territory, which means that they are more focused in the topics that they care about. So that may be something that would be of importance of thinking about the role. So one may say, well, but maybe these single authors, yes, it's diverse, but it's really not important. Nobody cares about those topics now, but at the same time, it is a diversity of topics, and some of these topics may be important later on. The relationship between the team size and the cognitive extent is inverse. So you can see there. So the smaller the team, the larger territory it covers, and then the larger it teams, the more focused it becomes in terms of what it is. And again, it does make sense. Like large collaborations like this, they're more focused. They don't cover everything, and there aren't that many teams like this, right? So it does make sense that they couldn't cover everything in a particular field. this method, and this is more for fun, and I haven't really published this, but if you're interested, you can apply this method of the cognitive extent measure to other units and not just the team sizes. So if you're interested in journals, actually the journal that covers the largest territory, or the largest, the largest cognitive territory, or the larger variety of topics, I'm like 2 more slides, thank you. So it's astronomy and astrophysics. So that one is the most of the, like, I don't know, I wouldn't say hodgepodge, that maybe it's negative, but it does cover the largest variety of topics. And the most selective, or the most focused one, is astronomical journal. It covers somewhat smaller territory. I'm not an astronomer. I don't know how to interpret that, but that's what I see. So some other thing is, oftentimes we say, oh, well, US is losing ground. All of these other countries are, taking over. And like, especially China. So people in China like, oh, like Chinese, they publish way more papers, and what are we going to do? Well, this is in astronomy, they do, and actually they appear only in the 2000s, like in terms of having significant, but you can see that even now, although the number has increased and they extended the territory, the cognitive territory extended, like covered by the Chinese teams, it's still much, much lower than the cognitive territory by. And again, it makes sense. They started more recently. You cannot develop everything at the same time. Like, you focus on the areas of excellence, and as you build those areas of excellence, you build other areas of excellence, and that's how you build. You can see that US still holds the largest cognitive territory. And again, these are more English language journals, so that may be a bias. You can see that there is some drop in the extent by both UK and France. So that's interesting. Both of these have somehow maybe dropped some of the topics. And then actually there is increase in the extent of the topics covered by Japan and China. But again, they are still covering only a subset. So to recap, there was a drastic change in the character of the team size distribution, and this model that I came up with, which is really the combination of the Poissonian distributed teams and them serving as a foundation of the extended teams, is a very good explanation. And I think this idea of having different types of problems, more regular problems, and problems that really require infrastructure building, for example, would require those extended teams. And the process that's driving this is cumulative advantage that's really driven by the productivity. And if you want to know what the cognitive extent is published, like, the large team are still more specialized. So science funding should acknowledge that there is still some role for individuals and small teams, but again, really understanding a better ecology, so to speak, of how these work. So that concludes my presentation. Any questions? Yes.
So your description of how really big teams form, where there's a core and then it creates, doesn't quite feel the way, for example, that LSST formed, where the LSST was a concept that was big from the beginning. A number of people, of course, grew, but it wasn't a small group that then decided to accrete. But we knew from the beginning that LSST would require a very large team. I wonder if you can comment on that.
So, okay, you may know that something will require a very large team, but when you started discussing it, how many people started the project?
It does, yeah. But those three were not publishing as scientists. I mean, LSST doesn't have any data. We don't have any LSST papers yet. The first LSST papers will have hundreds of authors.
So this may be based, but that's where the model, so LSST as such hasn't published yet, and when it publishes, it will go directly to the tail, right? But then leaders of the teams, and so the key here is that those extended teams do not come up, and these are the first papers for all of you. You haven't published before anything, you just come together, you get a couple of $1 million without publishing anything, and boom, like you get your first paper. And unfortunately, that's not. What works here is, and like I think looking at the core of the LSST, I would follow maybe the leaders. And again, it's not in the, it depends how you publish. So sometimes, some of the larger, I know for Galax, for example, that the way they published, there was the core team, the leadership team, and they were at the end of every single paper. I think it was a list of maybe 15 to 20 names. And then, so when I study this, I can look for the patterns. So if the last 15 or 20 names are always the same in the same order, that would be my core team. So that was a core Galax team, and I could probably, if LSST, when you publish, decide to do that, which I'm not going to start the conversation, but that is something that can be picked up in the publication, and then you can look at the members of the core team and see whether or the extended team, and see how they fared in the core teams. And they were probably, either had larger core teams or were more productive, or often both. I don't know, I hope that answers. But I think you're right, like it's really, when you think, like LSST, when it comes out, it would look as if it has always been big. And I think in science policy, they also think that that's the case. You just can build this, but there are years and years of experience, and it usually starts with smaller conversations. And here, it probably grew very quickly, right? Because if you have a really good vision also, and if you know what you need, you can build a large team very, very quickly. And that would be missed. But thank you, that's a really great comment.
So, two micro thoughts. One is that there is a traditional metric for this intellectual content. It's the citation rate after 50 years. This isn't terribly helpful. The other thought is that within astronomy, arguably the first extended team, first one that needed 3 people, was 1962. Anybody know? You're in the year? Bingo!
But that's like, but see, in the 60s, that was where the extended, yeah, and I think the citations, you're right, when I said that there aren't measures of the intellectual, sometimes the citations are, and then, like, there are, but it's 50 years. But again, there is a sense of acceleration in science, and like, for good reason, and we do want measures that may be more direct and quicker, because you can use this immediately and get some sense. But thank you, great comments.
Is this mic live? Yeah, I'm actually going to use it. I've done this before. My voice doesn't carry. Well, first of all, thank you for a great talk. And I'm going to say something that actually is a tremendous compliment, but it could be regarded as an insult. It seems to me the value of what you're doing is you know nothing about astronomy. And why I say that is you come in entirely externally and impartially and looked at the data and found these patterns, which I think is very, very important. So I want to comment on it personally, but I guess I'll ask first, it seems to me taking what you found and now I guess I'll call historical evidence of what's going on would be a very important next step. Have you thought about that? What do you want to comment on it? I mean, we can dive into more detail now and kind of put some flesh on your empirical model, so to speak.
So the question is, what are the next possible steps for these? Or?
Well, I would say, as we do in astronomy, I mean, you've made observational discoveries, I'll call them. Then usually we try to understand them theoretically, or that is at a deeper level. And I can imagine involving the techniques of the history of science and so on, as well as the sociology of science, we could take that and learn more about these dynamics in ways that you've just opened up.
That is true, but like for this particular, or the first paper, or the evolution of teams, in a way that goes deeper, but again, it's not sociological explanation, although it does have elements of productivity, which is a concept that sociologists do publish a lot. So, and that one is actually a model, a theoretical model that describes the dynamics of how these form. But you're right, this is so ideally, in the area of science or quantitative studies of science, some of you have, well, maybe most of you have heard of scientometrics, which is one branch of doing this sort of research, but scientometrics is usually concerned with evaluative indicators, and that's not something that I personally am mostly interested in. I'm interested in uncovering the principles of how science works, and this was one attempt. But again, this is this is just how the team size syndrome, but right. Thinking of the science as a whole, this is just one small, so think again, this is like ancient times for physics, when people try to model the whole universe and say it's flat, no, it's a turtle, no, it's not. But the problem was, you look at the whole universe and it's really too complex, and if you want to model the whole thing, it's really then too simplistic. And I think in the science of science, we need to identify what are the components, such as the team size, and then other things such as maybe collaboration in general, and then productivity, and try and understand the mechanisms such as this one, and then build more extensive teams using the knowledge also from ethnographists.
Right. Well, building on, one thing, just when you find a power law or whatever, we want to understand why and how what's the underlying cause. I think what we can already have information on is the sociology of how this came together. So in fact, Michael raised the point. Well, LSST started out big, of course, but it seems to me, really grew on the findings experience of the Sloan survey. There was a stepwise. So those are the kind of things. But that again, I think it's going to be very important for policy going forward, because now we're going to have to evaluate findings like yours in terms of cost, because in areas of limited budget. So I think you're adding great tools, but it's going to require some, I guess I'll say, insight and wisdom now to apply them well. And I think you've added a lot to that. So.
Yeah, well, thank you.
In my own career, I have to say, I started out as a single investigator, and I'm with the LSST. So this is the way to go. Thank you.
Okay, so there is hope for me too. Yeah, I know. I have a colleague, and this result on the collaboration or the rises of team I published as a single author. So when she introduces me, sometimes we have visitors and said, "Oh, and she's the person who wrote the single author papers on how teams grow." I'm like, okay.
We'll start with Adam Bolt in the back of the air.
Hi, thanks. So I just wanted to mention, maybe it's obvious, but I think it's worth saying explicitly that a big part of the LSST proposition, as I understand it, is partly, yes, that it goes directly to big science, but also that that it enables a lot of, 1,000 flowers of small teams blooming from the very beginning as well. So it's not just going to immediately influence that tail, but also the small team core as well.
Well, thank you. And I think now that I said that the small teams are seeds for big teams, and I think I can extend the model, because I think large collaborations like this probably they feed back to new core teams in a way, because I don't think everybody just works in this big one. So I think it's more of a feedback loop where you have such a large collaboration, and then it really feeds back to changing core teams or building new core teams, and then it feeds back to the extended team. Yeah.
Aaron, and then Tony will take the last question.
So, to continue in this vein, as someone who's been in 5 different big teams, I think sociologically only one of them grew with the kind of model you outlined. So, and since power laws are such a generic shape, and you can come up with a power law with many, many different models of how they actually might grow, I wonder if you have a prediction from your model that's different than the power law shape of the team size. Is there something else that predicts that you can search for that?
So to comment on the power laws, you're right. The problem with power laws is that we really do not understand very well the mechanisms that are driving. And as I said, before before I worked on this. The prevalent notion is that it's preferential attachment, and I intentionally call this cumulative advantage because I think it's advantage and I think it cumulates versus we just preferentially go to people and choose. And for this particular model, I tested 8 different mechanisms of types of preferential attachment, and the one that really worked best was the productivity of lead authors, not just the productivity of all of the authors. So there must be something about the productivity of the teams, like at least based on what I tested. So again, the thing would be, but I think the key is also the existence of these very small teams, which is completely ignored in most of the studies that just look at the power law tail. So the problem is, how do you account for 80% of people doing something here and like 0.06% of papers that are here and everybody is zooming in here because it's very interesting and it's novel. But you're right, I think like there is more room to figure out how exactly preferential or like the power law mechanism works. And I think it may be somewhat different, like the productivity really worked well for astronomy and physics, but it may be maybe in mathematics and others, it may be slightly different modifications of what is really driving the power law growth. Yeah, but thank you.
Thanks, Tony and Mr.
So, first, I have 2 comments. First, let me make a boring comment, but it's something that we should bear in mind, and that is that increasingly in science, huge collaborations have decided to publish in alphabetical order. Mm-hmm. So this will influence the statistics on the so-called lead author. So I find the power law interesting. I'm wondering if it's related to another power law, which is well known. So increasingly in science, and in particular in astronomy, there are big facilities that are making their data available widely. This leads to a power law, at least one that's well known, and that is the power law in data access. That and that has a slope of -1, which it's a little scary because that integrates to infinity. But it does have a slope of -1. And I'm wondering if that might actually be related to the power law that you have found. For example, in physics, in many areas of physics, it's still 2 or 3 author papers. Mm-hmm. Condensed matter, for example. Yeah. But in high energy physics, it started out already in the late 60s and early 70s as huge teams. And there, the tradition sociologically is to form big teams, and then you get the huge amount of data, and the teams get to feed on this data, very much like the Sloan survey and LSST eventually. And if you analyze the Sloan data access statistics, it's a power law. And I suspect LSST will be the same power law.
Well, thank you. That's a great comment. And I think when we think about how of the development of science in general, so yes, we are more collaborative, or like science in general and astronomy. But you're right that the access to data starts playing a big role. And you're going from the model where you apply as a single observer to the time and you fly, or you have to get to the location and you observe the data and you keep the data, now to these large surveys, right, that so many people can have access to. And I think it would be very interesting in astronomy to pair the two and see how such an unprecedented access to data, what is the effect on the teams and productivity. I think that would be very, very interesting.
Yeah, and it's not just big facilities. For example, in physics, there are these huge facilities now, photon sources, and they're just one or 2 users. Yes. Coming, and it's one or 2 authors.
It's like open data and data sharing.
It's very different sociology.
Yeah. No, and astronomy but I have to say that astronomy in that sense is unfortunately still fairly unique. I have to say in my field, it's very difficult to get the data. It's not that easy, but you are right. I think open access to really large amounts of data is a big game changer. And I think that would definitely...
And that leads to a power law, and I'm wondering if it's related to the one you found.
I think so. I would definitely check, but thank you for the comment. Thank
Let's
you.
thank our speaker again. So Stasa just let me know she is going to be at lunch in the coffee break. I know there's a lot of interest in continuing the conversation and asking her more questions, so please take a look out for her then. And so I realized, we're at a meeting, and a meeting about talking about meetings. It's a little bit like, I guess, for academics who can relate to this, being on the committee for committees. But yes. I am the chair of the committee for committees. But I bring a number of goals for this session. Unfortunately, this is unlike Victor's joke last night, where he played a little joke on the project team members and claimed he was going to make us all watch a training video, but instead it was a joke bloopers video. This is actually a talk about running efficient and effective meetings. And my goals for this session are to acknowledge and address a topic that I know is of importance to members of the scientific community, and also to acknowledge and address the project feedback that we've been receiving over the last year, and I'll highlight examples of these in a few slides. I'm also going to refer to some specific peer-reviewed studies to increase our awareness of some of the unconscious factors that can limit the efficiency and inclusiveness of meetings that we all run and participate in, and then suggest some specific strategies for improving communication and productivity, both in the scientific community meetings we have and the project team meetings we have, through running efficient and inclusive meetings. And so when I say meetings, right, there's lots of different types of meetings. I'm not going to be overly pedantic about things and really drill down on what I mean when I say meetings, but a lot of what I'm talking about are those regular meetings that we all spend too much of our time in every week, whether they're in person, on the telephone, or via a video conference. And so it is not my goal today to tell everyone in this room exactly how to do your job, how you should be running your science collaborations, or how you should be running your weekly team meetings, right? Instead, I'm trying to give some tips and strategies to make sure that we're all doing things with the level of excellence and rigor that we require to tackle our challenging scientific and engineering tasks. And a big part of that is running efficient and inclusive meetings, because they are such a primary way of communicating. And I'm not going to tell everyone exactly how to do their job for a lot of reasons. People in this room belong to a lot of different types of working environments and institutions. We collaborate with different team sizes and personalities. We have different goals. And as individuals, we all have our own personalities and styles that we need to make work for ourselves individually. And, this is a point. So as some of you know, in my past life, hi, I'm Beth Willman. I'm at LSST in the University of Arizona. Sorry, this is my 7th talk this week, so I assume we're all friends by now. So in my past life, I worked at a liberal arts college for 7 years. And when I first started my job, you show up at a new job, and everyone's telling you how to do your job, because they're mentoring you, right? I was like, oh, Beth, you got to use this technique in the classroom and that technique in the classroom and all these sorts of things. And I said, okay, yeah, I'm trying to remember this. The person who ultimately ended up becoming the best mentor that I've ever had, in part because his strategy was to absolutely deny the fact that he was mentoring me, in fact, explicitly disowning being a mentor and saying, I'm not mentoring you, Beth. One of our first meetings together, he said, you know what, I bet a lot of people are telling you how to teach your classes. I said, yeah, they are. And he said, oh, that's a bunch of BS. And he's like, don't let anyone tell you how to teach your classes, because we all have our different personalities, and we all have to figure out what we are going to do and how we're going to use our own strengths when we get up in front of the room. Just do your thing. And then, we just kept up the conversation and would talk to each other about how things were going. And that's, one of the ways that I found my own voice while at Haverford College. And I believe it's the same for any of these things, both as leaders of meetings and as participants in them. But there are some helpful rules of thumb that I can provide. And so we've heard, and I have experienced firsthand, that this is an important topic for the LSST team. This is incredibly common in all workplaces, that the number one time waster that is identified is time spent in inefficient meetings. And last year, just 1 year ago at LSST 2015, there were 2 different events that helped us realize that perhaps we should think about addressing how meetings are being run on the project. And one event was that we held a silent discussion on workplace culture. And one of the pieces of common feedback we received is, that's fine, you guys talk about this stuff every year. Fine, it's a challenge. Could you please actually give us some suggestions for how we can address these challenges? Give us some specific actionable ideas. And in our communication and climate survey for project members that we're reconducting this year, we heard that meetings are a primary way that we communicate, and it's critical because we are fast-paced and geographically distributed. But the meetings that we're having often don't feel productive, efficient, or inclusive of all viewpoints. And similarly, after the joint technical meeting in February, which was just a project team meeting that didn't include the scientific community, we held a workplace culture retreat for a small set of people on the manager and science leadership team. And again, we came back to the fact that ineffective meetings were defined as one of our biggest communication challenges. And so, again, right, being efficient and inclusive, it happens to be the case that my social values lead me to desire to be inclusive of people and want to be welcoming and create an environment like that. But, right, the national academies aren't writing studies about the critical need for us as a country to broaden the inclusivity and training of a diverse workforce looking ahead to the 21st century. They're not doing that because it's consistent with their social values. It is also fundamentally important to do things with excellence and rigor to recruit and retain a diverse set of people. We're missing out on a huge fraction of the population if we're not being fully inclusive of the voices of people independent of their gender identity or independent of what their cultural, socioeconomic background or age is, okay? And on the LSST time, we don't have time to waste. All of us feel that in our jobs every day. And LSST is hard. And if we don't hear all voices, we risk jeopardizing our commitment to the team, the scientific community, the funding agencies, and to the taxpayers that are giving us the money that enable us to build this machine. You know, my worst nightmare is, God forbid, we have a culture where junior members of meetings are afraid to speak up because someone's going to make them feel humiliated by saying, Beth, that's so obvious, why would you have said that? And junior team members stop speaking up and miss that important thing. Yeah, maybe everyone thought it was obvious all along, but on that one day, when that contribution was made in the meeting, everyone realized maybe there's an engineering decision or a software decision or a scientific judgment that we're taking that we're going to think a little bit differently about. And, you know, this is the perspective from the project team. I'm trying to help, you know, there's people from different sides of the LSST community, a lot of different stakeholders here, see two sides of where our communities are coming from. The issue of, you know, efficient meetings and inclusivity is also an important topic for everyone. And one of the things that makes me proud to be a member of the astronomical community is the increasing vocalization about our collective valuing of the urgent importance of increasing inclusiveness and diversity in our field. And this means we don't just need to think about what are the deliverables. People make those deliverables. And anyone who saw Frosty's talk on Tuesday saw this nice tweet she shared that I guess was shared by a bunch of people. I'm still figuring out the Twitter, which says, if you're an engineering leader and you worry more about your tech than your people, then you have your priorities backwards, because people build tech. And, you know, this repeats what I've already said, that as a scientific community, we also want and need to have a team, colleagues, and build a culture that is welcoming to folks from a wide range of backgrounds and with a wide range of communication styles. We want and need to benefit from the collective knowledge and experience of all of our colleagues. And this is more than just a recruitment and a retention issue. It's a recruitment issue, a retention issue, and an issue of once people are members of the team, we all need to learn how to listen to each other, even though not all of us have the same style of communicating, and not all of us bring the same experiences into the room, and not everyone is having the same experience as you. And so those of you that are on the project that receive project emails, this sentiment may be familiar to you, and it's appeared in a few of the project-wide emails we've sent over the last year, is just take that moment to remind yourself, not everyone is having the same exact experience as you, and how can we be considerate of that when conducting ourselves as meeting participants and as meeting leaders? Efficient and productive meetings 101. Okay, so here's a small list of things when I thought about, you know, for better or worse, I have been complimented at my efficiency and inclusivity in running meetings, and that's one of the reasons I'm giving this talk today. And so when I thought to myself, what do I think is sort of like the minimum bar to allow yourself to have a meeting? And there's exceptions to every rule. but this set of bullet points is what I consider to be the minimum bar. And I don't emphasize inclusivity as much here. I will spend a lot of the rest of the talk on that. So number one, the lead, I should have reversed the order of these two things. Every meeting should be owned by somebody. There should be a meeting lead. And everyone participating in the meeting should have the same understanding of who that person is. And the meeting lead is responsible for understanding and communicating the desired outcome for each meeting, even if it's a weekly meeting, and how that outcome will be accomplished. And everyone participating in that meeting should have an equivalent understanding of both the outcome and how you're going to get there. Remember, this is 101 stuff. You want to begin and end on time, and the meeting does not need to take the entire time you have scheduled for it. We are all curious people. We love talking about what we do because it's so interesting and cool. Stop. End the meeting. And of course, listen and be respectful. You know, this is my, I don't know, like 8th all hands meeting. So originally on the science side and now more on the project side of things. It's real easy when you've been working with people for, 5, 10, 15, 20 years to assume you kind of know what they're saying already and to stop listening or to interpret it through a filter that assumes you know what they're saying already. Everyone needs to remind ourselves of this. I'm so guilty of this, especially when I visit the in-laws. Okay. And my last 101 level point is, we do not all need to go to all meetings. We are all smart, we are all important, and we are all valuable. But we are not all such special snowflakes that we have to be everywhere all the time. And it's okay to delegate. Sometimes that knowledge transfer can be delegated. Sometimes you don't have to know everything just because you're interested in it. Does it really affect what you have to do or what your team members have to do that you have to communicate to them? And right, sometimes you have to go to a meeting because you're managed by somebody that tells you to, your department chair tells you to. I'm not telling you to flip the table. And well, you could speak truth to power. I approve of that. But think to yourself, if you have a choice, you don't need to go to all meetings. And if you weren't invited to a meeting, again, it doesn't mean you aren't smart, valuable, and awesome. It means we're all just running to get the science and our jobs done. Okay, so before I move on from 101 level, I want to give, so what do I mean? I think most of us are thinking, yeah, this is all super obvious. I do this all the time. And I think most of us probably also don't actually do this all the time. And again, I'm as guilty of this as anybody. So what's an example of how we can understand the desired outcome for a meeting and how that outcome will be accomplished? And so I think a really common level of fidelity that we would think is, I work in a geographically distributed science or project team collaboration. And so every week we have to tag up to keep everyone informed about the team's activities. So I think this is a really common type of meeting we all participate in. But that's not really specific enough, right? How many of us have these weekly tag up meetings and you're like, I either knew all this already, or everything I'm hearing is too technical and too irrelevant for me to really care about, right? So here's just maybe not the platonic ideal of the refinement of this. We have a geographically distributed collaboration. The work we do impacts our other colleagues' work. For example, sometimes one person or one team relies on the output of another person or another team's software. And the collective knowledge and experience of our colleagues can help us make progress on our work. We're going to take advantage of all of the skills that we have on our team. For example, we utilize similar engineering approaches to accomplish our goals. So how about the purpose of this weekly meeting is for team members to give brief updates on activities that might directly impact others on the team, where the plural on others is important, or that could benefit from consultation with the rest of the team. Thinking carefully about things like, when I'm giving an update, is it me, myself, or is it on behalf of others to the team so I can take responses and discussion back to my team? Efficient and productive meetings 201. These slides are now linked to the agenda page, so I won't actually read through everything on the next two slides. And I've sort of distilled what I thought were some of the most key points from a document that Lisa Hunter shared with Suzanne Jacoby and I. And I'm going to communicate with her after the meeting to see whether I may post this or a modified version thereof on the website. And so Lisa Hunter is at UC Santa Cruz, and she's the director of the Institute for Scientists and Engineer Educators. And she's also the chair of Aura's Workplace Diversity Committee. And so she's put together a checklist for running effective and inclusive meetings by the team that she distributes to her graduate students and collaborators. And so, as I said, I've pulled out some of, I think, the best examples here. And I want to emphasize this, take decisions during the meeting. You're a meeting leader. It is your responsibility to take decisions during the meeting and to design the meeting so that decisions can get taken. It's really easy to get down in the muck and down in the weeds, and you hit a wall and you hit a sticky spot, and you desperately want to say, let's figure this out next week. But you have to push through the sticky spots and then summarize decisions and actions and why you've taken them at the moment of the meeting. And we're all so busy, we think, gosh, I can't write that agenda in advance, or I can't write meeting minutes and circulate it. But think of the half hour you spend doing that, all the time it saves for you not having to revisit and have the same exact discussion week after week, which is something that I know that I get into, and it's easy to slip into that mode. And here are some of the other items in the running a meeting 201 checklist that I'll share with you. Okay. And so my last slide in this section of the talk is, what if you're a participant? Of course, you can support and assist the meeting leader in doing some of these practical things that can help the meeting be effective. And actually, before I go on, where one metric for measuring the value of a meeting is thinking, were decisions made, and do I understand what the next steps are and what to expect when I come to the meeting next week or next month? But this is basic stuff again. Participants, prepare for the meeting. You think you don't have time to, but that 5 or 10 minutes you spend preparing is going to save a lot of time in the future. Participate, offer your ideas when they are relevant to the discussion, and listen to yourself talking. Do most of the people in the room need to hear what you're saying? And are you saying it in a way that can be understood by the people who don't already know that information? Okay, and so the next and most of the rest of the talk, I'll highlight this question of unconscious challenges. I highlighted a lot of obvious challenges that we all face in just running meetings that are effective. But right, there's a lot of unconscious challenges that a significant body of peer-reviewed literature from economics to political science to social science to psychology have demonstrated can affect how equivalently we value voices in meetings and how seriously we process that information. And again, in my past life, one of the things that I did was develop and implement a seminar on the persistent lack of diversity in the sciences. And one of the focuses of this seminar was to take a look at the peer-reviewed literature to start understanding a little bit about how unconscious bias that we all have can impact or can decrease the diversity in the sciences, and to also think about increasing awareness of the unconscious biases as a key way to start mitigating them. And so I'll highlight both Space Telescope and NOAO have taken steps. I think Dara was leading this effort at NOAO to take a look at observing proposals submitted and see if there was a systematic difference in the acceptance rate depending on the gender of the PI who submitted the proposal. And it was found that there was a slight systematic bias where proposals with a PI who was a woman were accepted at a bit of a lower rate. And so an approach that's taken to this is the telescope allocation committees are now just shown the data and say, hey, be aware of this. This is something that's happening. We're not going to tell you what to do, but know that this impacts all of us. And so I'll highlight just a couple of different, there's an enormous number of papers that I, of course, can't go through all of them. And so, it's been shown that it's really hard for all of us to give all voices an equal opportunity. And so, a couple of effects that can impact our meetings is that it's been demonstrated that women are interrupted by both men and women more than men are interrupted, and that their ideas are sometimes not heard until they're remade by a man. And so I just pulled this one paper out of the Journal of Language and Social Psychology, which demonstrated that women were interrupted at nearly 3 times the rate of men in their controlled experiment. It was a little bit more often by women, actually, interrupting other women. Here's another example of a study. There's been a lot of work that's gone into understanding gender inequality in deliberative participations when teams get together to take decisions, when it's by majority versus a consensus approach. What type of approach and what type of running of the system tends to be more or less inclusive of people, of men compared to women. And again, if you're interested, you can go to my slides and take a look at those references. And there's also the issue of not just giving all voices equal opportunity to be heard, but then once people have the opportunity to share what they want to say, giving all voices equal weight. Again, we don't realize it, but everything we hear gets filtered through our past experiences and our own preconceived notions. And so there's a huge body of peer-reviewed literature that shows we all have unconscious biases that cause us to be in prejudice in favor or against certain people or certain types of groups. And it affects how seriously we take contributions of our colleagues without us even knowing about it. Right? It's not about anybody being bad or good. It's just this happens, and the literature has quantified that it happens. And so I highlight here just a couple of particularly well-known articles in this field that I think are interesting and easy reads. This very well-known study by Golden and Rouse took a look at auditions to join orchestras and shown that when you went from open to blind auditions, that the number of females accepted into competitive orchestra positions went up enormously. I didn't remind myself of the numbers this morning. Here's another one, written also in the American Economic Review. Are Emily and Greg more employable than Lakeisha and Jamal? Spoiler alert, yes they are, apparently. When enormous numbers of resumes are sent out that are identical but for the name on them, it has been demonstrated that unequivocally, if you have a white-sounding name versus a non-white sounding name, you are far more likely to get called in for an interview for a job, even with the identical credentials. And again, these studies have been done by many groups and have been very quantitative and systematic. Okay, so those are unconscious challenges. And again, there's also stuff that we all do that we're totally aware of, but we're sloppy about it, and it's hard to combat it. And so other conscious challenges to running an inclusive meeting, we all love talking, and it's harder to listen to ourselves. Sometimes folks willfully ignore perspectives of particular participants because of our history. And again, I'm not pointing fingers when I say that. We all fall into these patterns. And, you know, both as in my science hat on and my project hat on. It can be really hard to handle problem behavior. When someone's behaving in a way that you think could intimidate other team members from participating, you know, what do you do and how do you handle it? You know, my approach is to try to handle it in the moment or shortly thereafter. And it makes me feel sick every time I have to do it. It takes me an enormous amount of effort. It's very hard to do. And so everyone, you know, is like, well, can't you just go up and give a talk and tell us the recipe for handling like difficult people and hard situations? It's really different every time. It depends on your personality, on the other person's personality, the history in the team. Talk to people who you're close to and talk through different scenarios to help get advice on doing this. And I'm always happy to talk through different scenarios. LSST for project people has ombuds people that can also help you, talk through and role play how to handle difficult people. Oh, and then not doing anything about the unconscious issues at play, e.g. previous slides. Now that you're aware, willfully not doing anything to try to mitigate unconscious bias as a participant in the meeting and as a leader is you're now consciously not being inclusive. So I have just a couple more slides here. I was pretty speedy. So what are best rules of engagement for meetings? Right, I gave you this sort of recipe formulaic checklist that you can imagine going by. And this is a version of a slide I've showed a number of times. I think the last time I showed it was up at the Biosphere 2 to kick off that meeting for the Kavli funded study of the OER resources needed to maximize LSST science. And this was a meeting of different science teams. It was to be very collaborative and interactive. Our goal was to go through a challenging intellectual exercise to produce an excellent product that would give recommendations to the agencies and that we would be proud to show to the community as a representation of what the full community thought about these resources. And so I thought about how important it was to have a constructive meeting that aimed for rigor and excellence, and what it would look like for us to aim for rigor and excellence up there at the Biosphere 2. And this is actually a version of what I used to show in my Astronomy 101 courses at the beginning of the year, because I ran a very interactive class where people had to do a lot of group work, and I gave the students roles of engagement like this. We need to aim for a flexible, collaborative, and inclusive environment. And there are some examples in the checklist of how to do that. For example, looking around, noticing who's participating, and soliciting input from people who haven't offered their opinions yet, and for people that are speaking a lot to say, Beth, I've really loved all the points that you've given in this meeting already. Let's give a chance to, Pat or Michael to give their thoughts now. And people are actually more receptive to this often than you think. You have to be a bit persistent sometimes. To make it clear that questions and comments are welcomed. This was one that I like, and that Lucienne also has, and I'll show you in the next slides, as part of her rules for engagement at the LSSTC Data Fellowship Program. So there's a program that's run in New York City called the Recurse Center, which is this innovative, intensive program to teach people who don't know how to code or want to change, improve their coding skills to be better coders. And without making too much of a judgment statement, I think that, environments, fast-paced coding and software engineering environments don't necessarily have the best reputation for being inclusive and welcoming to newcomers. And so they have this really brief and nice set of social rules that they ask people who join the Recurse program to follow. And a couple examples of these are, don't feign surprise when you're interacting with people. I mess this up all the time. When you're saying, oh, you don't know what the stack is? Or, oh, you couldn't get the stack installed on your laptop? Okay. And then another one is to limit the well-actuallys. Often, different people in the room have more and less nuanced understandings of the different technical and scientific issues we're talking about. And sometimes adding nuance into the conversation is critically important to make progress and to take the decision. And sometimes adding nuance isn't actually necessary to accomplish the goals, just kind of shows that you know more than somebody else. And so, you might say, well, actually it's 8.4 meters, not 8.2, but, that's fine. And ironically, I think I broke both of these social rules during the biosphere meeting itself, and this allowed people to gently say, Beth. I said yes. I always try to make sure everyone is introduced. I can think actually of one meeting that just happened within the last 2 weeks where somebody had to say, hello, my name is. And again, I work to handle problem behavior in the moment or shortly thereafter. And I know Chris Montgomery reviewed Lucien's very nice code of conduct and engagement rules from that data science fellowship program. And I'll just give a couple highlights. Again, these are in the slides online, so you can read them in more detail if you'd like. And so she begins with an overarching code of conduct that's also drawn and points at these other codes of conduct that our national organizations and facilities have already written and thought about. She highlights shared value, right? The LSST Data Science Fellowship is building a cohort of people with technical expertise that they will themselves use in the future as data scientists and that they will then share and help the rest of the cohort with. And so there's values of shared responsibility, honesty, and respect that she's impressing upon these junior scientists. And I think all three of those are shared values that we would all like to say we share together as scientific and project collaborators. And then she suggests some principles of engagement to help ensure that we can meet these shared values. And some are similar to the ones I've already said, and some are a bit different, right? Raise all voices, pay attention to who's contributing, no feigning surprise, and none of well-actuallys, and then also no isms. No explicit racism, sexism, homophobia, transphobia, and other kinds of bias. It's not a joke. There's no jokes about this stuff. Just don't make the joke. Okay, my last slide is, something that I've really appreciated lately, and I've tried to acknowledge in a positive way some team members for doing, is checking yourself in the moment, right? Correcting your own real-time behavior works a lot. And it shows the people that you're in the room with, the person maybe who you just interrupted, or the person who you just put down. It's a good faith demonstration that you're trying. It's never too late to say, oh, you know what, I'm sorry I interrupted you, please go on. Or even at the end of the meeting, if it took you a while to kind of see what you were doing, say, you know what I said was disrespectful to your work, I'm sorry, I'm gonna try better next week. And then actually try better next week, and it might happen again. Keep trying better. And so thank you all very much for coming to this meeting about meetings, and that's all I have to say about this. And if anyone has a question or two, I'm happy to take it. Please, I think that's Gordon. Oh, no, that's Tim. Sorry. Another fellow with glasses.
The brief update section of the meeting, I find it would be somewhat more efficient if the person giving the brief update sent a paragraph around before the meeting so that we can just talk about what we actually covered. Otherwise, you spend 10 minutes listening to somebody ramble on maybe about what they did the week before, but you can cut that out completely if you could just give them somebody and then you get straight to the question.
Well, do it in a meeting, but you can do in other forums.
Yeah, so thank you. So two very good points there, and I'll repeat in case people didn't hear. Don't do in a meeting what you can do in another forum. And I know there's sort of, it can be a fuzzy line there. We get too many emails. What if I said an email to get lost in an email? But don't make people come together if you can do it another way. And then circulate materials before the meeting, both so people can prepare and so you can save time by not re-reviewing all the materials real time. Any other comments or questions along those lines or otherwise? Okay, great. And so we're going to have another plenary session after the coffee break. Again, I think I've received a few questions about what's going on tomorrow morning. At 9 a.m. tomorrow, people are free to follow up on work in the breakouts, either project breakouts or community breakouts. And we're asking everyone who led a community breakout session yesterday and today to ensure that somebody is going to be here at the 11 a.m. plenary to give a report back. Just a few minutes, a couple of slides, interpretive dance, whatever you need to do to report back at 11 a.m. And then someone will say some overall closing words for this week's project and community workshop as well. So thank you all. Please enjoy the coffee break. Oh, hey, Chris, thank you. Oh, hold on. Let me turn this off before I...
So, according to the schedule,